Hello, and welcome to the Sleepy Science Facts. I'm truly happy you're here. Maybe today felt long, or maybe you simply enjoy drifting off while thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body sink into rest. Let your mind move more slowly, and allow your thoughts to float. Because tonight, we're exploring the universe itself, not just a single galaxy or one bright star, but the vast, expanding whole. We'll travel gently from one calm fact to the next, learning about black holes, ancient light, dark matter, and distant galaxies. Some ideas may surprise you. Others may stay with you like a soft thought hovering at the edge of sleep. And if these peaceful explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you're ready, let's begin. The universe might be older than we think. Most current estimates place its age at about 13.8 billion years. This number comes from measurements of the cosmic microwave background and from how quickly space is expanding. But not every method agrees. Some observations of very ancient stars and faraway galaxies suggest they may be older than this estimate comfortably allows. Others question whether the assumed expansion rate is correct, or propose that dark energy might be changing over time. These tensions aren't resolved, and most astronomers still accept the 13.8 billion year figure. But the questions remain. Could the universe be older? Did we miss something fundamental? It's possible that what we call the beginning was only one chapter in a longer, stranger story. There are thousands of rogue planets drifting through space without stars. Not every planet belongs to a sun. Some worlds are completely unbound, floating alone through the galaxy with no star to warm them and no daylight to brighten their skies. These rogue planets may have formed in ordinary systems and then been flung outward by gravitational chaos. Others might have formed on their own, more like failed stars that never ignited. They are dark, cold, and nearly invisible unless they pass in front of background stars or reveal themselves with a faint glow in infrared. Astronomers estimate there may be billions of them in the Milky Way, perhaps even more than the number of stars. Each one is a silent world drifting in darkness, spinning alone in the vast spaces between suns. No sunrises, no sunsets, just endless night, broken only by distant starlight. The universe may recycle itself through endless cycles. The standard model of cosmology describes a universe that began with the Big Bang and will continue expanding, possibly forever. But some theories imagine a different rhythm. One where the universe goes through repeating phases of expansion and collapse. In these models, the cosmos doesn't end with a cold fading or a final crunch that stops everything. Instead, it resets. After reaching a certain point, it might bounce, collapsing inward, then rebounding into a new expansion. Each cycle could erase old structures, yet preserve faint traces of what came before. These ideas are speculative, but deeply intriguing. They suggest the universe may have no true beginning or end, only a rhythm stretched across unimaginable spans of time. One universe giving rise to another again and again. The oldest light we can see comes from about 380,000 years after the Big Bang. Before that time, the universe was like a glowing fog, so hot and so dense that light couldn't travel far without scattering. But as space expanded and cooled, it reached a turning point. Atoms formed, the fog cleared, and light was suddenly free to move. That ancient light is the cosmic microwave background, and we can still detect it today. It is the oldest direct signal we have, not from stars or galaxies, but from the universe itself, at the moment it first became transparent. The photons we observe now have been traveling for more than 13 billion years, stretched by the expansion of space into long, cool microwaves. The light is faint but ever present, a quiet glow carrying the memory of the universe's earliest clarity. Some stars may have planets made almost entirely of diamond. In certain solar systems, the chemistry is very different from our own. If a planet forms with more carbon than oxygen, and the pressures inside it are high enough, something remarkable can happen. Carbon can crystallize on a planetary scale. Astronomers have identified at least one candidate, an unusually dense world orbiting a pulsar, likely the remnant of a dead star. Based on its mass, density, and likely composition, the planet may be a crystalline form of carbon, essentially a giant diamond. It would be far too hot to sparkle, and it wouldn't look like a jewel up close. But deep beneath the surface, immense carbon lattices could stretch for thousands of kilometers. These strange worlds aren't common, but they remind us how diverse the universe can be. A planet made of rock, a planet made of gas, and sometimes a planet made of crystal. The universe may have no edge, only endless curvature. It's tempting to picture the universe as something with a border, an edge we could reach if we traveled far enough. But space doesn't appear to work that way. According to general relativity, the shape of space is determined by what it contains. And current evidence suggests the universe is either infinite or so vast and gently curved that it loops back on itself. If that's true, then in theory, you could travel in a straight line forever and eventually return to where you began, not by hitting a wall, but by wrapping around curved space. It's similar to how walking around Earth doesn't reveal an edge, only a globe. The universe may work in a similar way on a far grander scale. Not infinite in a simple sense, but infinite in journey. The Sun may once have had a twin, and that companion could still be out there. Some astronomers believe our Sun was born with a sibling star, formed from the same cloud of gas and dust more than 4 billion years ago. Many stars are born in pairs, and there's no strong reason to think the Sun was an exception. If this twin existed, it would have drifted away long ago, pulled apart by the slow gravitational tides of the Milky Way. It might still be orbiting the galaxy on a different path, unseen by us now. Some theories even connected this hypothetical twin, sometimes nicknamed Nemesis, to extinction patterns on Earth, though there's no solid evidence for that idea. Still, it's a haunting thought. Our Sun, steady and alone in our sky, may once have shared its beginning with a silent partner that vanished into the stars. A raindrop of neutron star material would weigh more than Mount Everest. Neutron stars are the collapsed cores of massive stars, dense remnants left after supernova explosions. They're only about 20 kilometers wide, yet their mass can be greater than the Sun's. The matter inside them is packed so tightly that a single teaspoon would weigh billions of tons. If you imagined a single raindrop made of neutron star material, it would be heavier than any mountain on Earth. That kind of density defies everyday experience. Atoms are crushed together so completely that electrons and protons merge into neutrons, forming a kind of superfluid neutron soup. Neutron stars are extreme objects, small, dark, heavy, and often spinning rapidly. And in their quiet mass, they hold the memory of stellar collapse, a final state where matter becomes almost pure gravity. Light from one galaxy can reach us from multiple directions. Sometimes light doesn't travel in a straight line. In regions where gravity is especially strong, near massive clusters of galaxies, for example, space-time itself curves. That curvature bends the path of light, the way glass bends a beam. This is called gravitational lensing. One of its strangest effects is that we can sometimes see multiple images of the same distant galaxy from different angles. These images can appear as arcs, smudges, or even complete rings. They aren't duplicates in space, but duplicates in vision. Different paths that the same light has taken through warped space-time to reach our eyes. In a few rare cases, astronomers have even observed the same supernova appear more than once, as its light arrived through different gravitational routes. It's a quiet reminder that in the universe, even light can wander, take the long way around, and still find its way home. The first stars may have burned 1,000,000 times brighter than the sun. The very first stars were unlike anything we see today. Born from the pure hydrogen and helium left after the Big Bang, these stars, often called population 3 stars, likely formed with no metals at all. That made them massive, intensely hot, and short-lived. Some may have been hundreds of times the mass of the sun. They would have burned through their fuel quickly, shining perhaps 1,000,000 times brighter than our star, then collapsing in spectacular explosions after only a few million years. None of these first stars survive today, but their brief lives changed everything. They created the first heavy elements, seeded the early galaxies with light, and set the stage for all that followed, including us. Their light is gone now, but their fingerprints remain, in the chemistry of ancient gas clouds and in the quiet structure of the early cosmos. Dark matter streams through your body as you sleep. As you lie still, dark matter flows silently around you. It isn't an invisible mist you could bottle or see. It's a form of matter that doesn't interact with light, doesn't reflect it, doesn't emit it, doesn't absorb it. Yet it has mass, and it responds to gravity. Our galaxy is surrounded by a vast halo of dark matter, and as Earth moves through that halo, trillions of dark matter particles are thought to pass through every square centimeter of your body each second. They don't collide with your atoms. They don't leave a trace. But they are there, ghost-like, ever-present, and essential. Without dark matter, galaxies wouldn't hold together, large cosmic structures wouldn't form, and the universe would look very different. We still don't know what dark matter is made of, but we know this much. It is part of your world, moving through you silently and continuously, even as you sleep. Some galaxies glow with almost no stars inside. In the quiet reaches of the universe, astronomers have found galaxies that contain gas and dark matter, but show little evidence of stars. Some may have lost their stars in violent gravitational encounters. Others may never have formed many stars at all. A few are nearly invisible except in certain wavelengths, appearing as faint smudges in deep sky surveys. These galaxies challenge what we think we know about how galaxies form and evolve. If they are rich in dark matter, why haven't they built stars? If they once had stars, where did they go? These dim, quiet systems drift through space like forgotten bones of cosmic history, reminding us that not every galaxy is filled with blazing light. Some simply exist, unseen and unanswered. The universe has a cold spot that shouldn't exist. In the cosmic microwave background, the faint afterglow left behind by the Big Bang, there is a region of sky that appears unusually cold. It isn't just slightly cooler than its surroundings. It is significantly colder and far larger than scientists expected. This cold spot spans hundreds of millions of light years, and its presence doesn't quite fit the smooth randomness predicted by early universe physics. Some researchers think it may be the imprint of a vast cosmic void. Others wonder if it could hint at something even stranger, such as a collision between our universe and another during the earliest moments of cosmic inflation. So far, no explanation fully satisfies the data. The cold spot remains one of the most quietly unsettling puzzles in cosmology. Not a dramatic anomaly, but a gentle whisper that something about our universe may not be exactly as it seems. The Moon is slowly drifting away from Earth. Every year, the Moon moves about 3.5 centimeters farther from our planet, roughly the speed at which fingernails grow. This slow retreat has been happening since the Moon formed around 4.5 billion years ago. Back then, it was much closer, and a day on Earth lasted only a few hours. The reason is tidal friction. As the Moon pulls on Earth's oceans and Earth spins beneath them, energy is gradually transferred outward, pushing the Moon into a wider orbit. It's a quiet, relentless process, invisible on human timescales, but unmistakable over geological ages. Far in the future, Earth and the Moon may become tidally locked, always showing the same face to one another. For now, the Moon continues its gentle departure, slipping away bit by bit as we turn beneath its distant glow. Binary stars can exchange their outer layers like dancers in close contact. In some binary systems, two stars orbit so closely that their outer atmospheres begin to touch. As the stars evolve, one may swell and spill material onto the other, creating a slow, spiraling transfer of gas. Sometimes this exchange is calm and steady. Other times it triggers bursts of light, rapid spinning, or even a complete merger. The physics is complex, but the image is strangely graceful. Two stars locked in orbit, brushing against one another, blending and changing. One may be stripped down to a glowing core, while the other grows swollen and enriched. Their fates are intertwined. Some of the most unusual objects in the universe, including certain supernovae and compact neutron star pairs, begin their lives as these quiet, touching binaries. A reminder that even stars can share, transform, and sometimes embrace. The vacuum of space is not truly empty. Even in the deepest, darkest reaches of space, far from any star or galaxy, the universe is never completely void. According to quantum physics, what we call empty space is filled with activity. Tiny pairs of particles and antiparticles blink into existence and vanish almost instantly. These quantum fluctuations happen everywhere, all the time, creating a restless background beneath reality itself. They can influence how particles move, affect the behavior of fields, and even contribute to the energy of empty space. This underlying activity is part of what gives rise to dark energy, the mysterious force accelerating the universe's expansion. So, when we imagine deep space as silent and still, that picture is only partly true. Beneath the quiet lies a constant dance of probabilities, a hidden hum of creation and disappearance, always present just below the surface of nothing. Time may flow at different rates in different regions of the cosmos. We often think of time as steady and universal, ticking forward at the same pace everywhere. But in reality, time is deeply connected to gravity, motion, and the shape of space-time itself. In regions where gravity is strong, such as near a black hole or a massive galaxy cluster, time passes more slowly compared to regions where gravity is weaker. This isn't just theory. It has been confirmed by experiments, satellites, and atomic clocks. Some cosmologists wonder whether time could also vary on even larger scales. Could different regions of the universe experience slightly different rates of time due to the way space expanded in its earliest moments? The idea is speculative, but it opens quiet and strange possibilities. In a universe governed by relativity, even time may not be absolute. It may stretch, slow, or bend, shaped gently by the space through which it flows. The Milky Way has a hidden halo far larger than the visible galaxy. When we look at images of the Milky Way, we see a bright spiral of stars, dust, and gas. But surrounding this familiar structure is something vast and mostly invisible, the galactic halo. This enormous sphere of diffuse gas and dark matter extends far beyond the visible edge of the galaxy, reaching distances many times greater than the disk itself. The halo contains ancient star clusters, stray stars, and immense amounts of unseen mass. It is held together by gravity, shaped by past collisions and mergers, and plays a quiet role in keeping the galaxy stable. We can't see it directly, but we infer its presence through the motion of stars and the bending of light. The Milky Way, it turns out, is just the glowing heart of something much larger, wrapped in invisible arms. We have detected light from a galaxy that formed just 200 million years after the Big Bang. The universe is about 13.8 billion years old, but light takes time to travel. As it moves through expanding space, it is stretched and slowed. That's why we see distant galaxies not as they are now, but as they were long ago. Using the James Webb Space Telescope, astronomers have identified light from a galaxy that existed only 200 million years after the Big Bang, a brief moment on cosmic timescales. That light has been traveling toward us for more than 13.5 billion years. The galaxy itself is small, faint, and primitive, but it offers precious clues about how the first structures formed. Observing it is like peering through a narrow window into a time when darkness was only just beginning to give way to stars. The large-scale structure of the universe resembles a neural network. When astronomers map the positions of galaxies across enormous distances, a surprising pattern appears. Galaxies are not scattered randomly. Instead, they gather along long, thread-like filaments, with vast empty regions called voids in between. This interconnected structure stretches across billions of light-years and is known as the cosmic web. When viewed from far enough away, it looks uncannily like a neural network, similar to the patterns found in the human brain. dense clusters of galaxies resemble neurons, and the filaments resemble connecting fibers. The resemblance is purely visual. The universe is not thinking. Still, there is something quietly beautiful in the fact that the largest structure we know and the structure inside our own minds can end up looking so strangely alike. Stars can sing through the vacuum of space. There is no air in space, so sound as we know it cannot travel. But stars still vibrate. Deep inside them, pressure waves move through hot gases like seismic waves through a planet. These oscillations cause stars to subtly pulse and tremble. Scientists can detect these vibrations by observing tiny changes in a star's brightness or surface motion. The study of these stellar vibrations is called asteroseismology, literally the seismology of stars. Each star has its own set of internal frequencies, shaped by its size, structure, and age. By listening to these vibrations, astronomers can learn what is happening deep inside a star. It is a kind of cosmic echolocation, a way of hearing stellar music across vast distances, even though the song itself is silent to human ears. Some stars are older than the galaxies they inhabit. Galaxies are not formed all at once. They grow over time, merging with smaller systems and gathering stars and gas from many places. Because of this, some stars within a galaxy can be older than the galaxy's current shape. They may have formed in much smaller galaxies that later merged into a larger one. These ancient stars are often found in the outskirts of galaxies, or in globular clusters, tightly bound groups orbiting far from the center. Some are more than 13 billion years old, nearly as old as the universe itself. They carry the chemical signature of a younger cosmos, when heavy elements were rare and only the simplest atoms existed. These stars are like fossils, quiet survivors from before the galaxy fully assembled. Their light is ancient, and their stories began before much of what we know had even formed. There are galaxies without dark matter, and we still don't know why. Dark matter is thought to be the invisible glue that holds galaxies together. It explains why stars in the outer regions of galaxies move faster than expected, and why galaxies cluster the way they do. But in recent years, astronomers have discovered galaxies that seem to break this rule. These systems behave as if they contain little to no dark matter at all. Their stars move as though only visible matter is present. This discovery was unexpected and doesn't fit neatly into current models. Some scientists suggest that dark matter may have been stripped away during past collisions. Others wonder if our understanding of dark matter itself is incomplete. Either way, these strange galaxies remind us that the universe still holds deep uncertainties, and that what we assume to be universal may not apply everywhere. The sun rings like a vast, resonant bell. Deep inside the sun, sound waves ripple through the plasma, bouncing between layers and setting the entire star into subtle, continuous vibration. These waves aren't sounds we could hear. They are slow-pressure oscillations, far below the range of human hearing. With sensitive instruments, however, scientists can detect them and use them to study the sun's hidden interior. This field is known as helioseismology. By observing how the sun vibrates, researchers can map its inner structure, measure how it rotates, and trace the movement of hot gas deep beneath the surface. In this sense, the sun behaves like a musical instrument, vast and complex, always resonating. We simply need the right tools to listen. What we hear helps us understand not only our own star, but stars throughout the universe. Galaxies follow invisible filaments made of something we cannot see. The largest structures in the universe are not made of stars or glowing gas. They are shaped by dark matter. Over billions of years, dark matter formed enormous filaments stretching across space, and galaxies formed along these structures like beads on a string. We can't see the filaments directly, but we can infer their presence by watching how galaxies cluster and how light bends as it passes through these regions. These filaments can stretch for hundreds of millions of light years, connecting vast clusters of galaxies. Between them lie enormous voids, regions with very little matter at all. Dark matter acts like a hidden scaffolding for the visible universe, guiding how galaxies grow and where they travel. And yet, despite its influence, we still don't know what dark matter truly is. The structure is there, immense and unseen, quietly holding everything together. Space itself can stretch faster than the speed of light. Under normal conditions, nothing can move through space faster than light. But space itself is not bound by that rule. In the earliest moments after the Big Bang, space expanded so rapidly that distant regions were carried apart faster than light could travel between them. This wasn't motion through space, but the expansion of space itself. Even today, distant galaxies aren't flying away because they're moving quickly. They are receding because the space between us is stretching. If a galaxy is far enough away, that stretching causes it to recede faster than light, which means we will never see it again. This doesn't violate physics. It's a quiet consequence of how space-time behaves on cosmic scales. The universe doesn't rush. It expands calmly, steadily, and beyond what we can ever follow. Our solar system moves through space in a graceful spiral. It's easy to picture the planets orbiting the sun in neat, flat paths. But when you zoom out, something more intricate appears. The sun itself is moving, orbiting the center of the Milky Way at nearly 1,000,000 kilometers per hour. As it travels, the planets follow along, not just circling the sun, but tracing a long, spiraling path through space behind it. This combined motion creates a helical pattern, like a twisting ribbon or a cosmic corkscrew. Everything is in motion: the planets, the sun, the stars, and the galaxy itself. There is no true stillness in space, only continuous, gentle drift. Even as you sleep, you are moving, tracing slow spirals through a galaxy in motion, wrapped in layers of orbits within orbits. Even emptiness has a temperature. If you travel far from stars, planets, and galaxies into deep intergalactic space, you might expect absolute cold. But even the vacuum has a temperature. It is about 2.7 Kelvin, just a few degrees above absolute zero. This faint warmth comes from the cosmic microwave background, the cooled afterglow of the Big Bang, stretched and softened by billions of years of expansion. This radiation fills all of space. No matter where you go, it is there. It is the quiet thermal signature of the early universe, still present, still measurable. In the far future, it will cool even more, but it will never disappear completely. Even in the deepest emptiness, the echo of heat remains. Quantum fluctuations may have shaped the entire universe. At the smallest scales of reality, far smaller than atoms, the universe behaves unpredictably. Tiny fluctuations in energy can appear and vanish in an instant, a direct result of quantum uncertainty. Many cosmologists believe these brief, random fluctuations were stretched to cosmic scales during inflation, the rapid expansion that occurred just after the Big Bang. As space expanded at unimaginable speed, these tiny variations grew into large differences in density. Those differences became the seeds of structure, the places where matter would gather, where galaxies would form, and where stars would ignite. In this way, the grand structure of the universe may trace back to fleeting quantum events, the trembling of near-nothingness giving rise to everything we see today. Some stars die in slow, rhythmic pulses. Not all stars end their lives in sudden explosions. Some fade gradually, and in their final stages they can pulse, swelling and shrinking in regular cycles. These are known as variable stars. Their brightness changes over time, sometimes steadily, sometimes slowly, like a long, measured heartbeat. The pulses are caused by changes in the star's outer layers, gas expanding and cooling, then collapsing and heating again. Some stars complete a cycle in days, others in months or years. These rhythmic stars have been used for decades to measure distances across space. Because their pulse patterns reveal their true brightness, they are quiet timekeepers of the cosmos, marking the passage of stellar life with long, gentle breaths. Earth resides inside a vast bubble of hot gas. If you could see the universe in wavelengths beyond human vision, you would find that our solar system sits inside an enormous cavity called the local bubble. It stretches hundreds of light years in every direction and is filled with thin, hot gas. This bubble was likely carved out by ancient supernova explosions, stars that died long ago and blasted shock waves through surrounding space. Over time, those explosions cleared out material and heated what remained. Today, our solar system drifts quietly within this low-density region, surrounded by a shell of warmer gas and dust. It's not something we can feel, and it poses no danger, but it is there. A quiet chamber shaped by violence long past, now part of the gentle background of our galactic neighborhood. There is a vast empty region behind the Great Attractor. The Great Attractor is a mysterious region of space with immense gravitational pull, drawing entire galaxy clusters, including our own, slowly toward it. But beyond this massive concentration lies something even stranger, a region known as the dipole repeller. This area appears unusually empty, a massive cosmic void stretching across hundreds of millions of light years. Its emptiness seems to push galaxies away, just as the Great Attractor pulls them in. Together, these two features create a subtle gravitational balance that shapes the motion of our local universe. We are drawn forward by unseen mass and pushed back by emptiness. It is a reminder that in the cosmos, both presence and absence can guide the paths we follow. Neutrinos pass silently through Earth and through you. At this very moment, trillions of tiny particles called neutrinos are passing through your body, and you never feel a thing. Neutrinos are incredibly light, nearly massless particles produced in enormous numbers by the sun, exploding stars, and even the earliest moments of the universe itself. They rarely interact with ordinary matter. Most of them pass straight through planets, oceans, mountains, and people without leaving any trace at all. A few are detected deep underground, where rare collisions allow scientists to study them. But the vast majority move through everything unnoticed. These particles are everywhere, all the time, silently streaming through space and matter alike. They travel close to the speed of light, barely touching anything, reminding us that the universe is full of motion even when everything feels still. The most massive stars can collapse directly into black holes without an explosion. We often imagine the death of a massive star as a brilliant supernova, lighting up the galaxy in a final flash. But for the heaviest stars, the end can be strangely quiet. Some stars are so massive that when their fuel runs out, their cores collapse inward so completely and so quickly that even the outer layers fall straight in. No bright explosion, no dramatic farewell. The star simply disappears, leaving behind a black hole. This process is known as direct collapse. Astronomers have observed stars that seem to vanish without warning, as if their light simply blinked out. It's a reminder that not all cosmic endings arrive with fireworks. Some slip away in silence. Galaxies can orbit one another like moons around planets. We often think of galaxies as isolated islands in space, but many exist in small groups where they interact and even orbit one another. Our own Milky Way has dozens of smaller companion galaxies. The large and small Magellanic Clouds are the most familiar examples. These satellites move around the Milky Way like moons, tracing long, slow paths through space. Over time, larger galaxies can pull stars from their companions, forming long streams of light stretching across the sky. Eventually, smaller galaxies may be absorbed entirely. These interactions unfold over billions of years, slow and graceful, almost imperceptible on human timescales. In the quiet of deep space, even galaxies can keep one another company. The universe's brightest explosions may come from collapsing magnetic stars. There exists a rare and powerful kind of event known as a magnetar-driven hypernova. A magnetar is a type of neutron star with a magnetic field trillions of times stronger than Earth's. If a massive star collapses into a magnetar and releases its energy rapidly, the result can be an explosion far more energetic than a typical supernova. These events may be responsible for some long-duration gamma-ray bursts, brief flashes of intense radiation that can outshine entire galaxies. The explosion lasts only seconds, but its light can travel billions of light years. It is one of the most extreme phenomena the universe can produce, created by a small, dense object wrapped in invisible magnetic force. The edge of the observable universe is not the edge of the universe itself. When we look out into space, there is a limit to how far we can see, about 46 billion light-years in any direction. This boundary marks the edge of the observable universe. It isn't a wall or an ending. It simply represents the furthest distance light has had time to reach us since the Big Bang, accounting for the expansion of space. Beyond that boundary, the universe almost certainly continues. We just cannot see it. Because space is expanding faster and faster, some regions are already moving away from us so quickly that their light will never arrive, even given infinite time. The observable universe is like a bubble of vision, not the full size of reality, just the part available to us. Beyond it, more galaxies, more stars, perhaps endlessly. Some galaxies launch jets of plasma millions of light years long. At the center of many galaxies lies a supermassive black hole. When matter falls toward it, not all of that material disappears. Some of it becomes trapped in powerful magnetic fields and is flung outward in narrow, focused jets. These streams of plasma travel at nearly the speed of light and can extend far beyond the galaxy itself, stretching for millions of light years. We detect them in radio wavelengths as vast glowing lobes. Galaxies that produce such jets are known as radio galaxies, and their outflows are among the largest structures in the universe. It is a strange irony that some of the most powerful emissions in existence arise near black holes, where light itself struggles to escape. There is a star in the Milky Way that orbits in the wrong direction. Most stars in our galaxy move in the same general direction, following the rotation of the Milky Way. But a few do not. At least one known star travels on a retrograde orbit, moving against the galactic flow like a swimmer going upstream. How did it end up that way? One possibility is that it formed in a smaller galaxy that merged with the Milky Way long ago. Another is that it was flung into its unusual path by a gravitational encounter, perhaps involving a black hole or dense star cluster. Whatever the cause, it serves as a reminder that not everything in the galaxy follows the same pattern. Even in a vast cosmic system, there are wanderers moving to their own rhythm. The center of the galaxy contains molecules that resemble the scent of raspberries and rum. This may sound like a joke, but it's real. Astronomers studying a dust cloud near the center of the Milky Way detected a molecule called ethyl formate. On Earth, this compound is associated with the flavor of raspberries and the aroma of rum. Space itself doesn't carry scent the way air does, but the presence of these molecules reveals the surprising complexity of interstellar chemistry. Clouds between the stars contain alcohols, sugars, and precursors to amino acids. It isn't life, but it is the kind of chemistry life might grow from. Space may not smell sweet or sharp, but it quietly carries the ingredients of complexity, drifting unseen between the stars. One galaxy is on a slow collision course with the Milky Way, and it has already begun to touch us. The Andromeda Galaxy is our nearest large galactic neighbor, about 2.5 million light-years away. That distance is shrinking. In roughly 4 billion years, Andromeda and the Milky Way will begin to merge. Interestingly, their outer halos, vast regions of gas and dark matter, are already overlapping. In that sense, the two galaxies have already started to meet. The future merger will not be a violent crash, but a long, graceful blending. Most stars will pass by one another without colliding. Over time, the two spirals will form a single, larger elliptical galaxy. This slow cosmic meeting is already underway, unfolding over billions of years. The cosmic microwave background still surrounds you. Every part of the universe, including the space around you right now, is filled with a faint glow left over from the Big Bang. This radiation was released when the universe was about 380,000 years old, when atoms first formed and light was free to travel. That light has been moving ever since, stretched into microwaves by the expansion of space. Today, we detect it as an almost perfectly uniform background in all directions. It cannot be seen or felt, but sensitive instruments reveal it as a quiet cosmic whisper. It is the oldest light we can observe, a signal from the universe's early childhood, still echoing through space and time. Some supernovae are powered by invisible collapse rather than light. Supernovae are famous for their brilliance, vast explosions that can briefly outshine entire galaxies. But not all supernovae announce themselves with light. Some are known as failed supernovae. In these events, a massive star's core collapses into a black hole, but the outer layers never explode outward in a visible flash. Instead, they fall inward, feeding the newly formed black hole in silence. In rare cases, astronomers have observed stars that appeared stable and then suddenly vanished. No bright explosion, no lingering glow, just darkness where a star once shone. These events suggest a collapse so complete that almost all the energy is swallowed. The violence is real, but it is hidden from view, reminding us that not every cosmic death leaves a visible mark. Deep within gravity's grip, there are galaxies made mostly of gas and dark matter. We often picture galaxies as bright spirals or glowing ellipses filled with countless stars. Yet some galaxies contain very few stars at all. These dim systems are composed mainly of gas and dark matter, making them difficult to detect. They may appear only as faint smudges or reveal themselves indirectly through gravitational effects. Some may be failed galaxies that never formed many stars, perhaps because their gas was stripped away or heated too early in cosmic history. Others may represent temporary stages in galactic evolution. What they share is subtlety. No dazzling arms, no bright cores, just quiet gravitational presence. They remind us that not all galaxies shine. Some simply exist. Black holes can collide and merge in slow cosmic dances. When two black holes orbit each other, they send out ripples in space-time known as gravitational waves. As energy leaks away, the black holes spiral closer and closer until they merge into a single object. These collisions produce no light, but they release powerful gravitational waves that travel across the universe. In 2015, scientists detected such a signal for the first time, confirming a prediction made by Einstein a century earlier. Since then, dozens more have been observed. Each detection tells a story of massive objects colliding in distant galaxies long ago. These mergers are silent to the eye, but immensely powerful, briefly making space-time itself vibrate. Some stars die slowly, fading over billions of years. Not every star ends its life in a sudden explosion. Smaller stars, like our Sun, follow a quieter path. After exhausting their nuclear fuel, they expand into red giants and shed their outer layers into space. What remains is a white dwarf, a dense, hot core that no longer produces energy. It simply radiates its leftover heat into the darkness, very slowly. Over billions of years, a white dwarf cools and dims, eventually becoming a black dwarf. The universe is not yet old enough for any black dwarfs to exist. Every white dwarf that has ever formed is still glowing somewhere, quietly fading. Their deaths are less like fireworks and more like embers cooling over cosmic time. Time slows dramatically near a black hole. In Einstein's theory of general relativity, gravity doesn't just pull on matter. It bends space and time themselves. The stronger the gravitational field, the more slowly time passes relative to regions with weaker gravity. Near a black hole, where gravity is extreme, this effect becomes profound. If you could orbit just outside the event horizon, time for you would pass far more slowly than for someone far away. Minutes near the black hole could correspond to years elsewhere. This phenomenon, known as gravitational time dilation, has been measured in weaker forms using satellites and precise clocks. Near black holes, it becomes extraordinary. They don't merely trap light, they stretch time itself. The space between galaxies is colder than any place we can create on Earth. Far from stars, planets, and gas clouds, the vast voids between galaxies are astonishingly cold. Temperatures there hover just a few degrees above absolute zero, around 2.7 Kelvin. This is colder than any natural environment on Earth, and colder than most laboratory conditions we can produce. The chill comes from the near absence of matter and energy. There is little to hold heat, only a sparse scattering of atoms and the faint microwave glow left over from the early universe. These intergalactic voids are the quietest places we know, enormous and empty, stretching across millions of light years, holding only the faint whisper of creation. The universe has grown more transparent as it ages. In its earliest moments, light could not travel freely.
The universe was filled with a hot plasma, a dense fog of electrons and atomic nuclei that scattered photons constantly. As the universe expanded and cooled, electrons combined with nuclei to form neutral atoms. Suddenly, light was free to move unhindered. This event, known as recombination, occurred about 380,000 years after the Big Bang and released the cosmic microwave background we still observe today. Since then, the universe has continued to grow clearer. Matter spread out, stars and galaxies formed, and there was less and less to block a photon's path. Space, once opaque and glowing, now allows light to pass almost freely. We have captured the shadow of a black hole. In 2019, the Event Horizon Telescope released the first direct image of a black hole's shadow. The black hole itself cannot be seen, but the glowing ring of hot gas swirling around it reveals its presence. This particular black hole lies at the center of the galaxy M87, about 53 million light-years away. The image shows a dark circular region where no light escapes, surrounded by radiation twisted by intense gravity. Creating the image required years of global collaboration, linking telescopes around the world to act as a single Earth-sized instrument. The result was more than a photograph. It was a quiet triumph, offering our first direct glimpse of one of the universe's most mysterious objects. You can see an entire galaxy with your naked eye. Most galaxies are so distant that even powerful telescopes reveal them only as faint smudges. But one galaxy is visible without any equipment at all. The Andromeda Galaxy can be seen from dark locations in the northern hemisphere as a soft, hazy patch in the sky. It lies more than 2.5 million light-years away, meaning the light you see left it long before humans existed. Andromeda contains roughly 1 trillion stars, more than twice as many as the Milky Way, and it is slowly moving toward us.
It is remarkable to look up and see an entire galaxy using only your eyes. A vast island of stars drifting quietly in the dark. A tiny detector once heard the whisper of colliding black holes. In 2015, an observatory called LIGO detected a faint ripple in spacetime from more than 1 billion light-years away.
The signal came from two black holes merging, sending gravitational waves across the cosmos. These waves are extraordinarily subtle. When they reach Earth, they stretch and compress space by less than the width of a proton. Yet with delicate instruments, scientists can detect them. LIGO and similar observatories act like cosmic ears, listening to the deepest murmurs of the universe. The detection confirmed that even in the silence of space, massive events can send out waves that travel vast distances, reaching a small detector on a quiet planet. Some regions of the universe are expanding away from us forever. The universe is expanding, and that expansion is accelerating. As space stretches faster and faster, some galaxies are being carried away so quickly that their light will never reach us. Even if we waited forever, the distance between us and those galaxies would grow too fast for light to cross. They have already passed a cosmic point of no return, slipping beyond what is known as the event horizon of the universe. Over immense spans of time, more and more of the cosmos will fade from view, not because it disappears, but because its light can no longer arrive. This change will be slow and unnoticed in daily life, but over billions of years, it means the visible universe will gradually shrink, quietly letting go of distant realms. Some black holes may be primordial, born before any stars existed. Most black holes form when massive stars collapse. But there is another possibility. Black holes that formed in the earliest moments of the universe, before stars and galaxies came into being. These are called primordial black holes.
They may have formed from tiny fluctuations in the extremely dense conditions shortly after the Big Bang. Regions where gravity briefly overwhelmed everything else. Some of these black holes could be very small, while others might have grown over time. We have not directly detected any yet, but if they exist, they could help explain dark matter, influence the formation of galaxies, or reveal new physics from the universe's earliest seconds. They would be older than stars, older than galaxies, silent relics from the birth of time itself. Entangled particles may connect distant corners of the cosmos. Quantum entanglement is one of the strangest features of physics. When two particles become entangled, their properties remain linked no matter how far apart they are. Changing one instantly affects the other, even across enormous distances. This does not allow information to travel faster than light, but it does suggest that reality at the deepest level is profoundly interconnected. Some physicists believe entanglement may play a role in the structure of space-time itself, perhaps even helping to hold space together. Particles created in the early universe may still be entangled today, stretched across the expanding cosmos. If so, invisible threads could be linking distant regions, quiet quantum echoes from the dawn of time, still present in the emptiness between galaxies. The vacuum of space has quantum pressure. Even in a perfect vacuum, where there are no atoms, no particles, and no radiation, there is still energy. Quantum physics tells us that empty space is never truly empty. Instead, it is filled with restless fluctuations. Fields shift slightly, particles appear and disappear, and energy never quite settles. This activity creates what is known as vacuum energy. On the largest scales, this energy may help explain dark energy, the mysterious force driving the universe's accelerating expansion. Unlike ordinary matter or radiation, vacuum energy does not thin out as space expands. It remains constant,
causing space to stretch faster as there is more of it. It is a strange and gentle idea that the more emptiness exists, the stronger its influence becomes. Black holes emit faint heat over unimaginably long times. Black holes are famous for trapping everything, even light. Yet according to quantum theory, they are not completely dark. Physicist Stephen Hawking showed that black holes can emit a tiny amount of radiation, now called Hawking radiation. This process occurs near the event horizon, where pairs of virtual particles form. Occasionally, one particle escapes while the other falls inward, allowing the escaping particle to become real. Over enormous timescales, this causes the black hole to lose mass. For a black hole with the mass of the Sun, this evaporation would take far longer than the current age of the universe, trillions upon trillions of years. It is the quietest ending imaginable, not an explosion, but a slow fading into nothing. Most matter in the universe exists as plasma. When we think of matter, we usually picture solids, liquids, and gases. But the most common state of visible matter in the universe is plasma. Plasma is an ionized gas in which electrons and atomic nuclei move freely. It fills stars, flows in the solar wind, drifts between stars, and stretches across the spaces between galaxies. Most of the visible matter in the cosmos exists in this form. Plasma behaves differently from ordinary gas. It responds strongly to magnetic fields, carries electric currents, and flows in complex patterns. On Earth, we see plasma in lightning, flames, and neon lights. In space, it is everywhere, glowing softly and shaping much of what we observe. Gravitational waves travel at the speed of light. Gravity does more than pull objects together. It can ripple.
When massive bodies, such as black holes or neutron stars, collide, they send waves through space-time itself. These gravitational waves stretch and compress space as they move outward, traveling at the speed of light. Detecting them required decades of technological development, but today we can measure these tiny distortions from Earth. Each wave carries detailed information about distant events, revealing the masses involved, how fast they were spinning, and how violently space-time was distorted. Gravitational waves are silent to human senses, but they are real and measurable. Gentle tremors passing through the deep structure of the universe. The cosmic web connects galaxies across unimaginable distances. On the largest scales, galaxies form a vast network known as the cosmic web. They are arranged along invisible filaments of dark matter and gas, stretching between clusters like threads. Where these filaments intersect, enormous superclusters of galaxies arise. Between them lie vast voids, regions nearly empty of matter. This structure cannot be seen all at once, but it emerges from large surveys of the sky. It resembles a woven fabric, a foam, or even the branching patterns of neurons. It is the universe's grand architecture, not random, but shaped by gravity over billions of years, like something grown rather than built. The James Webb Space Telescope can observe galaxies that no longer exist in the same form. Because light takes time to travel, telescopes show us the past rather than the present. The James Webb Space Telescope was designed to look farther than ever before, and in doing so, it also looks deeper into time. Some of the galaxies it observes may have merged, faded, or transformed long ago. Yet their light is still arriving, carrying a frozen image of what they once were. Astronomy is filled with this quiet strangeness. We never see the universe as it is now, only as it was at different moments in its long history. Every deep image is a time capsule,
a gallery of light from worlds that may already be gone, light from distant galaxies left before Earth existed. When you observe a galaxy billions of light years away, you are not only seeing distance, but age. The light began its journey long before Earth formed, before the sun ignited, before our planet took shape. Some of the galaxies we observe today sent out their light more than 10 billion years ago. That light traveled through expanding space, stretched and softened along the way until it finally reached our instruments. In this sense, astronomy allows us to watch the ancient universe unfolding in real time. The stars we see may no longer exist, but their light remains, a gentle reminder that the night sky holds stories older than Earth itself. Entire galaxies can be hidden behind clouds of dust. Even something as massive as a galaxy can be concealed. In some regions of space, thick clouds of interstellar dust block the light behind them. This dust is not like household dust. It is made of tiny grains of carbon and silicates drifting through cold molecular clouds. When a galaxy lies behind one of these clouds, much of its visible light is absorbed or scattered. Astronomers can only detect it by observing in infrared, radio, or X-ray wavelengths, which can pass through the dust more easily. Using these methods, entire galaxies have been discovered where empty sky was once assumed. In space, darkness does not always mean absence. Sometimes it simply means something is waiting to be seen in the right light. Some galaxies are surrounded by perfect circles of bent light. When a massive galaxy lies directly between us and a more distant object, its gravity can bend the background light into a near-perfect ring. This phenomenon is known as an Einstein ring. It occurs when space-time itself curves the path of light, acting like a natural lens. These rings are rare and striking, glowing loops suspended in space, created not by motion, but by alignment and gravity. The light forming the ring may come from a distant galaxy, a quasar, or even a supernova. Einstein rings help astronomers measure the mass of galaxies, map dark matter, and study the early universe. They are quiet illusions shaped by the geometry of space itself. The universe may be infinite. When we look at the sky, it feels natural to wonder whether there is a boundary somewhere, an ultimate edge to everything. But current observations suggest that space may extend without limit. We can only observe a finite region, the observable universe. But beyond that, space may continue endlessly. No center, no edge, just more galaxies, more stars, and more distance. If the universe is infinite, most of it will always lie beyond our reach. We will never see it, no matter how far we look or how long we wait. An infinite universe does not imply infinite variety, but it does suggest an endless, quiet vastness stretching on without conclusion. Cosmic rays constantly strike Earth from deep space. Every second, high-energy particles known as cosmic rays hit our planet. Some originate from the sun, others from distant supernovae, black holes, or even more mysterious sources beyond our galaxy. These particles are often protons or atomic nuclei accelerated to extraordinary speeds. Most are deflected by Earth's magnetic field or absorbed by the atmosphere. But some reach the surface, and a few even pass through your body. In small amounts, they are harmless, but they are a reminder that space is not empty. It is filled with motion and energy, invisible messengers traveling vast distances from ancient cosmic events. There may be no such thing as before the Big Bang. The phrase sounds natural, but it may not make sense. According to general relativity and many cosmological models, time itself began with the Big Bang. That moment marked not only the beginning of matter and energy, but also the start of space and time as we understand them. Asking what came before may be like asking what lies north of the North Pole. Some theories propose a previous state or universe. Others describe a quantum realm where time behaves differently or does not exist at all. In many models, however, the Big Bang was not an explosion in space. It was the beginning of space itself. Astronomers once mistook quasars for nearby stars. When quasars were first discovered, they appeared as faint points of light, almost indistinguishable from ordinary stars. But their spectra were strange, and their brightness varied in unexpected ways. It took years to realize these objects were not stars at all, but the luminous centers of distant galaxies. A quasar is powered by a supermassive black hole surrounded by a disk of hot, infalling gas. As the gas heats up, it shines with incredible intensity, sometimes outshining the entire galaxy that hosts it. The first quasars observed were so distant that their light had traveled billions of years to reach us. They looked small and simple, but turned out to be some of the brightest objects in the universe. Our local group of galaxies is falling toward a hidden region. The Milky Way is not stationary. Along with Andromeda and dozens of smaller galaxies, it belongs to a loose collection called the Local Group. This group is drifting through space toward a massive gravitational anomaly known as the Great Attractor. Beyond that may lie even larger structures, such as the Shapley supercluster, partially hidden behind the dense plane of our own galaxy. We can measure the pull of these distant masses even when we cannot see them clearly. It is as if our entire cosmic neighborhood is sliding toward something enormous, wrapped in shadow, guided by gravity we can sense but not fully observe. We are living in the universe's stellar springtime. Right now, the universe is filled with stars that are forming, burning, and exploding. But this phase is not eternal. In the earliest hundreds of millions of years after the Big Bang, there were no stars at all. The first ones formed in darkness, ignited their surroundings, and began the long process of cosmic evolution. Star formation increased, reached a peak, and has been slowly declining ever since. We now live in a kind of cosmic spring. Stars are still being born, but fewer than before, and more than will form in the distant future. One day, the last stars will ignite, and after that, the universe will slowly grow dark. For now, it remains bright enough to wonder and quiet enough to rest. In the distant future, stars will stop being born. Star formation depends on cold clouds of gas collapsing under gravity. Over time, this fuel is consumed, blown away by supernovae, or heated until it can no longer form stars. Billions of years from now, galaxies will run out of usable gas. Existing stars will age and fade, one by one. First, the massive blue stars will vanish, then stars like the Sun, and finally, the long-lived red dwarfs. The universe will not end suddenly. It will dim gradually, quietly, until only remnants remain. Most matter in the universe is invisible. When we observe the cosmos, the stars, galaxies, and glowing nebulae we see represent only a small fraction of what truly exists. The majority of matter does not emit or reflect light. This hidden substance is known as dark matter. Although we have never detected it directly, its presence is undeniable through its gravitational influence. Galaxies rotate faster than visible matter alone can explain. Light from distant objects bends more than expected. Massive clusters of galaxies remain bound together by gravity stronger than their luminous mass allows. All of this points to an unseen component, outweighing ordinary matter by more than 5 to 1.
Dark matter forms an invisible framework that shapes the universe, holding everything else in place. Light from the first galaxies has been stretched by cosmic expansion. As light travels through space, it does not simply move forward unchanged. Because the universe itself is expanding, the space that light moves through stretches as well. This stretching lengthens the wavelength of light, shifting it toward the red end of the spectrum. The light emitted by the earliest galaxies billions of years ago has been stretched from visible wavelengths into the infrared. This effect, known as redshift, allows astronomers to measure both distance and cosmic age. The more stretched the light, the farther and older its source. With powerful instruments like the James Webb Space Telescope, we can now observe this ancient light, softened and reddened by its long journey through expanding space. The universe may be a hologram. This idea sounds like science fiction, but it is taken seriously by some physicists. The holographic principle suggests that our three-dimensional universe might be described by information encoded on a distant two-dimensional surface. This concept arises from studies of black holes, where all the information about what falls inside appears to be stored on the surface area, not the volume. Some theories propose that the universe as a whole could operate in a similar way. What we perceive as depth and space may emerge from deeper informational rules. This idea remains unproven and abstract, but it gently reminds us that reality, even when it feels solid, may be more subtle than it appears. Space itself may be granular at the smallest scales. To our senses, space seems smooth and continuous. Even under microscopes, it appears empty and unbroken. Yet some theories of quantum gravity suggest that space-time may be composed of tiny discrete units, like pixels in an image. This smallest meaningful scale is called the Planck length, unimaginably small. At that level, smooth space may dissolve into a foamy, grain-like structure. We currently lack the tools to observe this directly, but if true, it means that everything, from galaxies to thoughts to sleep itself, unfolds within a universe that has structure all the way down. Some stars spin faster than kitchen blenders. Certain stars rotate at astonishing speeds, so fast that their equators bulge outward. Neutron stars take this to an extreme. A type known as a millisecond pulsar can spin hundreds of times per second. This means an object only about the size of a city rotates faster than a blender blade. These stars emit beams of radiation that sweep across space like cosmic lighthouses, flashing with incredible regularity. Many are locked in tight orbits with companion stars, pulling in matter and spinning even faster. They are among the fastest rotating objects in the universe, and also some of its most precise clocks, ticking silently across the darkness. The universe may end in a long, quiet fade. Early cosmologists once wondered if the universe might collapse back in on itself. Today, evidence points toward a different fate: endless expansion.
As galaxies drift farther apart and star formation slows, the night sky will grow darker. Existing stars will burn out. Black holes will slowly evaporate. Energy will spread thinly across space. This scenario is known as heat death. It is not a sudden catastrophe, but a gradual cooling and quieting of everything. Over unimaginable spans of time, the universe will approach stillness, not with fire or ice, but with silence. Some galaxies generate powerful superwinds. In certain galaxies, especially those with active black holes or intense star formation, enormous winds blow outward from the center. These galactic superwinds can carry gas, dust, and even young stars far into intergalactic space. They are driven by radiation, magnetic forces, and the combined energy of supernova explosions. Over time, these winds can strip a galaxy of the gas needed to form new stars, leaving it calm and dim. At the same time, they spread heavy elements into the cosmic web, seeding future generations of stars and planets. In this way, galaxies breathe, drawing matter inward, igniting stars, and then exhaling into the void. The far future of the cosmos resembles a dark, endless ocean. Trillions of years from now, galaxies will have drifted so far apart that each will appear alone in the darkness. New stars will no longer form. Old stars will fade away. Even the faint glow of white dwarfs will disappear. What remains will be scattered remnants, black holes, and the thin echo of ancient light. Over immense time, black holes will evaporate, and matter itself may decay. Eventually, only particles drifting through empty space will remain. This future is known as the heat death of the universe. It is not an ending with drama, but a vast stillness, like a cosmic sea without waves, wind, or shore. We may live inside a giant cosmic void. The universe is filled with clusters of galaxies, and between them lie enormous regions called voids. These vast spaces contain very little matter and can span hundreds of millions of light years. Some scientists propose that our region of the universe lies within one of these voids, an area less dense than average. If true, this could help explain certain observations, such as measurements of cosmic expansion or subtle patterns in the cosmic microwave background. Living inside a void would not affect daily life, but it would mean that what feels like emptiness is part of a much larger structure, the quiet interior of a cosmic bubble drifting through invisible gravity. Magnetars possess magnetic fields trillions of times stronger than Earth's. A magnetar is a type of neutron star, the collapsed core of a massive star. Although only about the size of a city, its magnetic field is unimaginably powerful. Earth's magnetic field guides compasses.
A magnetar's field is so strong it could erase data, distort atoms, or tear matter apart from great distances. These fields slowly decay over time, but while they last, magnetars can release intense bursts of high-energy radiation. A single flare, even from across the galaxy, can be detected on Earth. They are among the most extreme objects known, dense, silent, and wrapped in invisible force. The largest known structure in the universe is a giant quasar group. In 2013, astronomers identified an enormous structure made up of quasars, the bright, active centers of distant galaxies.
This structure stretches over 4 billion light-years across. It is known as a large quasar group, and its sheer size challenges our understanding of how uniform the universe should be on the largest scales. According to standard cosmology, matter should be relatively evenly distributed beyond a certain distance. Yet this structure appears larger than that theoretical limit. Whether it represents a true physical connection or a rare statistical alignment is still debated. Either way, it reminds us that the universe may be more complex and more interconnected than our models currently predict. Black holes can twist space-time into a funnel of time. A black hole does more than trap light. It warps space-time itself. As you approach the event horizon, space curves inward and time slows dramatically. To an outside observer, time near the black hole appears to crawl. At the very edge, it nearly stops. This warping creates a funnel-like geometry, narrow and steep, where all paths lead inward toward the singularity. Near this boundary, space and time begin to exchange roles, with inward motion becoming a direction in time rather than space. This is not just metaphor. It is the geometry written directly into the fabric of reality by gravity. Some regions of the universe will never be able to communicate with each other again. Because the universe is expanding, and that expansion is accelerating, some regions are already being carried apart faster than light can travel. This means that even in infinite time, light from those regions will never reach us. Likewise, any signal we send will never arrive there. Over cosmic time, more and more of the universe will pass beyond this limit. Each galaxy will become an island, surrounded by darkness. This does not violate the laws of physics. Nothing is moving through space faster than light. Instead, space itself is stretching calmly and relentlessly, separating distant regions forever. Gold is forged in the most violent stellar events. Gold is rare, not only on Earth, but throughout the universe. It cannot be created in the cores of ordinary stars. Instead, it forms during extreme events such as the collision of neutron stars or certain powerful supernovae. In those moments, atomic nuclei are crushed together under intense pressure, creating heavy elements like gold, platinum, and uranium. These atoms are then scattered into space, mixed into clouds of gas, and eventually incorporated into new stars, planets, and living beings. Every piece of gold carries the memory of a cosmic catastrophe, a trace of stellar violence that has settled quietly into matter we now hold in our hands. Light stretches as it travels through expanding space. When light journeys across the universe, it does not simply move through a fixed stage. The stage itself is expanding. As space grows, the wavelength of light stretches with it, shifting toward the red end of the spectrum. This effect is called cosmological redshift. The light is not losing energy through collisions. It is being gently stretched by the growth of space itself. When we observe distant galaxies, we are seeing not only how far away they are, but how much the universe has expanded since their light began its journey. Each photon carries a quiet record of cosmic history written into its length. There are ancient sound waves frozen into the structure of the universe. In the early universe, before atoms formed and light could travel freely, matter and radiation were tightly coupled in a hot plasma. In this plasma, gravity and pressure created oscillations, waves of compression and expansion similar to sound waves in air. When the universe cooled and became transparent, These waves were frozen into the distribution of matter. Today, we can detect their imprint as a preferred spacing between galaxies. This phenomenon is known as baryon acoustic oscillation. It is a subtle but powerful signal, a fossil record of sound from a time before stars existed, still shaping the large-scale structure of the cosmos. Galaxies can be consumed by larger ones without leaving a trace. Over cosmic timescales, galaxies do not remain isolated. They interact, collide, and sometimes merge. When a small galaxy approaches a larger one, gravity can tear it apart. Its stars are stretched into long streams and absorbed into the larger galaxy's halo. Eventually, the smaller galaxy becomes indistinguishable from its host. Astronomers have found evidence of such events in our own Milky Way, in the form of stellar streams arcing across the sky. This process is known as galactic cannibalism. It is slow and graceful rather than violent, a quiet assimilation that shapes galaxies over billions of years. Some stars flicker gently like fireflies. Not all stars shine with steady light. Many vary in brightness, pulsing or dimming in regular patterns. These are known as variable stars. Their changes can be caused by internal pressure waves, surface activity, or eclipsing companions. To an observer on Earth, they appear to flicker softly in the night sky. Some complete their cycles in hours, others in years. These variations are not random. Many follow precise rhythms that allow astronomers to determine their true brightness and measure vast cosmic distances. Stars do not only burn, some breathe. Some black holes roam through space alone. Not all black holes sit at the centers of galaxies. Some wander freely. A black hole can be ejected from its birthplace by gravitational interactions, flung outward during galaxy mergers, or launched by the recoil of another black hole collision. Once free, it drifts silently through space, emitting no light unless it encounters gas or disturbs nearby stars. These rogue black holes are difficult to detect, but they are likely numerous. They move through darkness without orbits, companions, or homes, carrying only mass and motion, gravity without a visible source. Black holes themselves can be kicked across galaxies. When two black holes merge, the gravitational waves they emit are not always perfectly balanced. If more energy is sent in one direction, the newly formed black hole can receive a powerful recoil, known as a gravitational kick. This can send it racing through space at thousands of kilometers per second. Some may be launched entirely out of their galaxies, destined to wander intergalactic space. Others settle into wide, drifting orbits. These black holes are silent travelers, propelled by the memory of their own violent creation. Some dead stars crystallize into cosmic diamonds. When a star like the Sun dies, it sheds its outer layers and leaves behind a dense core called a white dwarf. Many white dwarfs are made primarily of carbon. Under the immense pressure of gravity, that carbon can crystallize. In effect, some stars become enormous diamonds. These stellar remnants are roughly the size of Earth, yet far more massive, glowing faintly as they slowly cool. Some even vibrate, ringing softly like a struck bell. A white dwarf is a quiet jewel of the cosmos, a crystal born from ancient fire, drifting through space as it slowly fades. Most of the universe's history still lies ahead. 13.8 billion years sounds vast, but compared to the full lifespan of the universe, it is only the beginning.
Stars are still forming. Galaxies are still assembling.
Black holes are still active. In the distant future, these processes will slow and end, but that chapter has not yet begun. We live in a brief, luminous era when the universe is alive with motion and change. The past is enormous, but the future is far larger still. Supernova remnants continue expanding for thousands of years. When a massive star ends its life in a supernova, the brilliant flash is only the beginning. The explosion sends a powerful shock wave outward, and that wave keeps moving for centuries or even millennia. As it expands, it sweeps up gas, dust, and debris, forming glowing shells known as supernova remnants. These structures shine across many wavelengths, from radio to X-rays, and their shapes tell the story of the original blast. Some form delicate filaments, others turbulent clouds. The Crab Nebula is one such remnant, still spreading outward from a supernova observed on Earth nearly 1,000 years ago. These remnants are the slow breaths of dead stars, continuing long after the initial light has faded. Even a single planet can bend light. Gravity bends light not only on the scale of stars or galaxies, but even planets can cause this effect. When a planet passes directly between a distant star and Earth, it can briefly act as a tiny gravitational lens. This phenomenon is called microlensing. It is subtle and rare, but powerful enough to reveal planets that would otherwise remain invisible, even planets in other galaxies. A slight brightening, a gentle curve in a star's light, and a hidden world is revealed. The planet itself may be dark and cold, but its gravity leaves a detectable mark. The universe once glowed with warm orange light. In the early universe, everything was hot, dense, and filled with radiant energy. As space expanded and cooled, there came a moment when atoms formed, and light was finally free to travel.
At that time, the universe would not have appeared black or blue, but softly orange, glowing evenly in all directions. This warm light has since been stretched by cosmic expansion into the faint microwave glow we detect today as the cosmic microwave background. Long ago, the entire universe glowed like a dim ember, slowly fading as it expanded into the darkness we see now. Some regions of the universe cool more slowly than others. As the universe expands, it cools overall, but not uniformly. Regions with more matter or trapped radiation retain heat longer. Galaxy clusters, for example, contain enormous reservoirs of hot gas that remain warm for billions of years. More isolated regions cool faster. These differences influence how structures form, how long stars live, and how galaxies evolve. Even in a universe governed by simple physical laws, local variations persist. Cooling happens unevenly, like weather rather than machinery, textured and gradual. It may be possible for new universes to form. Some theories suggest that entirely new universes could emerge from our own through processes we do not yet understand, perhaps through quantum fluctuations, black holes, or other extreme conditions. These events would likely occur far beyond our ability to observe.
If they happen, they might appear as expanding bubbles of unfamiliar physics separating from our reality. We do not know whether this has ever occurred or will occur in the future. Still, the idea remains that creation may not be finished, that beginnings could still arise quietly within the vast darkness. The universe still carries echoes of its first moments. In the fraction of a second after the Big Bang, space expanded violently in a phase known as inflation. Tiny quantum fluctuations were stretched across the cosmos, becoming the seeds of galaxies, stars, and planets. Those early ripples left echoes behind. We see them today as subtle temperature variations in the cosmic microwave background. One day, we may even detect them as primordial gravitational waves. The universe may seem calm now, but it still hums faintly with the memory of its first vibration, like a bell softly ringing long after it was struck. You are a way for the universe to know itself. The elements that make up your body were forged in stars. Carbon, calcium, iron, all were created in stellar furnaces and scattered through space before becoming part of life. You are not separate from the universe. You are a moment of it made aware. In you, the cosmos has grown eyes and curiosity. Through you, it observes itself, wonders at itself, and dreams. Even now, as you drift toward sleep, the universe continues that quiet dreaming. Thank you for spending this time here, drifting through space and time with me. We have traveled across immense distances, past dying stars and newborn galaxies, listening to ripples in space-time and echoes from the beginning of everything. And through it all, there was you, breathing slowly, thoughts softening, perhaps already asleep. The universe is full of motion and mystery, but it also holds stillness. It holds light and gravity, but also peace. And the fact that we can explore it gently, piece by piece, in quiet moments like this, is something truly beautiful. Wherever you are now, whether awake or drifting beyond thought, may your dreams be calm. May your rest be deep, like starlight resting on dark water. And may you carry with you, even faintly, the memory of a universe that glows not only above you, but within you. If you are still awake, you may continue to the next chapter. And if you wish to drift into more stories like this, softly told and filled with wonder, you are always welcome to return. Good night.